Hola amigos! Today we're going to learn how to make this Niagara effect that pushes the particles around to create these interesting looking patterns called Chladni figures. The particle effect itself uses a material with some exposed parameters that we can customize to change the shape of the pattern displayed. And because of the way that the material and the Niagara system are implemented, we can edit those parameters in runtime and the effect will update accordingly without resetting the particle's position. But before we start, let me talk just a bit about these cool patterns. You might recognize these shots from the intro to the show Rings of Power. Most of them are actually practical, made with sand on top of vibrating plates. These patterns owe their name to the German physicist and musician Ernst Chladni, the inventor of the technique used. However, it was the French mathematician Sophie Germain the first to find the equations that describe the figures. Since then, many other smart people have come up with variations on these formulas, and a bit of searching around gives plenty of research papers on this topic. We still have to use some of this math, but don't worry, I won't bore you with all the details and we'll skip to the meat and bone of the matter. Also, the science YouTuber Steve Mould recently made a video about this too, explaining the basic mechanics of these patterns in a very easy and understandable way. Go check out that video after this one if you're still interested in learning about this. And now, without further ado, let's get started by creating a new material and diving right into it. In the material properties, we can leave the domain and blend mode as they are, but change the shading model to unlit. We only need some values from this material, so we don't care about all the other channels. I also changed the preview to a plane, so it's easier to see what we're doing. Now, we'll need a few values for our equation, starting with the UVs. You can keep the regular UVs or center them, remapping the values to a -1 to 1 or -0.5 to 0.5 ranges. In my case, I prefer the center symmetry, so I will multiply by 2 and subtract 1 from the texture coordinate. Next, we need to add two scalar parameters. These two, which we'll call m and n, are the main values that define the pattern, and basically control the number of nodal points on each axis. I know it sounds complicated, but we'll see how they work with a practical example in just a moment. And finally, the last value that we need is pi, the constant, not the food. This next bit can be easily done with a custom node, but I will keep it in the graph so we can make some quick changes later on. First, we need to multiply both m and n parameters by pi. Then multiply each one again by one of the components of the UVs. And finally, take the cosine of that. So after doing this on both parameters, here at the top I have the cosine of m times pi times u, and at the bottom the cosine of n times pi times v. Now we can multiply both of these together and output the result to see what we have. This gives us this sort of distance field with these repeating squares. If I change the values for m and n, you can see how those are affecting the number of divisions on each axis. Cool. Now we have to make some space and copy-paste all of these math nodes that we added and repeat all of the previous operations but replacing the u and v connections. Let me explain. So if on the first set I had m times pi times u, in this second one it will be m times pi times v. And the same goes for the second parameter. In this group it will be n times pi times u. If I preview this second group of nodes and change any of the parameters so they don't have the same value, you can see that we are basically inverting the x and y axis here. Now we can add or subtract these two values and output the result. Perfect, we almost have our patterns going, especially when m and n are lower than 1, but these values are not in the correct range yet. Truth is, most of the black areas in this image are not 0 but negative values. To remap them, we simply have to divide by 2 and add 0.5 to the result. We can think of this almost like a distance field to the patterns that we want to make. The next step will be to filter this so we can choose the thickness of the lines. This next part is going to need us to run a for loop, and there's not really a clean way to do this using regular nodes, so we have to use a custom node. Let's set it up before we add the code. We have to add two inputs. One is the thickness value, which we will get from a new scalar parameter, and the second one our distance field. Let me finish connecting this, and this time instead of typing the code in the material editor, I will open a separate notepad so it is a bit easier for you to copy. First, we need to initialize the float value that we will return and set it to 0.0. Next, in the for loop, we run a few passes with a range of deltas, where we're getting the difference between the original distance field value and the delta, and use that in a smooth step between the difference minus the thickness and the difference plus the thickness, using the thickness itself as the alpha. This is similar to other filters that we've seen in other tutorials, but here we are also accumulating the results of the whole smooth step of the range before returning the result. Note that we don't need the curly braces on the for loop since we only have one line. You don't have to tab it though, that is just to make it easier to read. Also, some of you might have noticed that the deltas are biased towards the positive values. You can experiment with different delta ranges, but I like the results that you get using these numbers. Now we can copy this code to the custom node, and if everything is correct, we should have our patterns. This looks super noisy, but it is only because the coefficients are set to values too high. Once they are set to something more reasonable, the results are looking promising. And as I mentioned before, feel free to use different numbers and experiment with this math. You can even animate some of these parameters over time to get really trippy effects too. As a quick demonstration, I can temporarily replace one of the parameters with a debug time sign node so we can see the effect of animating these values. Another change that we can make is to replace the cosines in the function for sines, which changes the symmetry mode. I personally like both of them, so I'm going to add a boolean parameter so I can quickly swap them in the material instance later. The easiest way to do this is to add a static switch node for each one of the sine-cosine pairs, connecting the true input to the sines and the false input to the cosines, or vice versa. Then, create a static bool parameter and connect it to the value input on all of the switches. After doing this, we can toggle between both symmetry modes with a single click, which is quite convenient. So now we have a fun material with a bunch of customizable properties, and as I said earlier, you can add more changes to all of this math and still create very interesting shapes. Next, we want to use this in our particle effect, and for that it will be useful to think of this grayscale image as a scalar field. Particles in this field will be pushed towards the areas with the highest values, which means that we need to somehow calculate the direction from each point to those areas, or in different words, we need to calculate the field gradient using our good old friends the partial derivatives. We can define this field gradient as the direction towards the neighbor with the highest value, which in our case we will reinterpret as a velocity field to apply to the particles, making them converge on the lines. Let's add both ddx and ddy nodes to the graph. As we've seen many times now, these are the partial derivatives of the values, representing the rate of change on the x and y axis. That is why their horizontal or vertical lines fade out if we preview any of the two derivatives. And this rate of change is precisely what we want, so we can combine them with a makeFlow2 into a two-dimensional vector and get this colorful version of the lines, which are the velocities that we will impart onto the particles. And note that this is showing only the vectors that are pointed towards the bottom right, because the top left directions are represented by negative values. We need to keep those values as they are, but we can temporarily visualize the entire range by adding an absolute value node. If we do that, we can see now how the velocity values are converging from both sides of the lines. And finally, I'm not 100% this is necessary, but I'd had issues with negative values in the past, so just to make sure that the engine doesn't convert them while we're not looking, we can go to the material parameters and check the option Allow Negative Emissive Color, which should stop any behind the curtain shenanigans from happening. Here I'm changing the default thickness value to get a bit more range on the velocity field and less defined lines, but we can always change those parameters later. And now we're done with this material, and we can create an instance of it so we can change the parameters in runtime without recompiling the entire shader. However, in Niagara we cannot sample materials but textures, so we have to create a render target as well. In the texture properties of the render target, I left all the parameters as defaults, but increased the resolution to 1024 square. You can also change the format to RG16F to save some memory, since we're only using the red and green channels of the texture. Now we need a way to update this render target, and the easiest method is to create a quick actor blueprint that we can instance. We can make something more elaborate, but the purpose of this tutorial is to show the effect, so I will simply make it update the texture once every second, and not worry about animating the parameters or any other fancy tricks. Start with a delay on the tick event, followed by these three nodes in sequence: begin draw canvas to render target, draw material, and end draw canvas to render target. Next, connect the context variable in the begin and end draw calls. In the first node, select the render target that we just created, or drag and drop it from the content browser, and do the same with the material instance in the draw material node. Finally, pass the size from the begin draw to the screen size parameter in the second node. Once everything is connected, we can drag the actor to the viewport and place it on the scene, and press play to test it out. If things work as they are supposed to, you should be able to open the render target, change the material instance parameter, and see the texture updating up to a second later. Perfect. The render target is changing in runtime as we expected. I think that is pretty fun just to mess with these parameters and see the results, and I reckon that I could spend hours tweaking the math and adding more parameters, but we have the texture that we were looking for, so it is time to move on to the particle effect. Create a new Niagara system from an existing emitter and select the empty template. After giving it a name, we can head over to the editor and start working on it. Starting with the emitter properties, we can make this one use its local space. We will move the emitter around, and this way we won't have to worry about offsets. We are going to sample a texture later, so we also have to change it to be a GPU sim and add fixed bounds. I set mine to a -1000 to 1000 range, just to make sure that we had plenty of room in the render bounding box for this tutorial, but we can go back and reduce this number later. Next, in the emitter state, change the mode to self and behavior to once. I increased the loop duration, but that was only to have a longer preview in the editor before the sim resets, since in this window the loop is controlled by the timeline. We can now add a spawn burst instantaneous and set the count to a medium-high number, like 50,000. In the initialize particle module, we can leave all parameters as defaults for now, but I want really tiny particles, so I will set the sprite size to a uniform 1. We will change these for meshes later on, so we don't have to make any other changes right now. Next, we need to keep the particles alive forever, so uncheck the Kill Particles when lifetime has elapsed option in the particle state module. Let's move on to the fun part now. We're going to sample a texture, and we have to tell the engine the UV coordinates for that sample, which we will store as a particle parameter. Add a set new or existing parameter to the particle spawn stage, then make a new 2D vector, which we will call UV. When we create the particles, we want them uniformly distributed, so we can set this parameter to a random 0 to 1 vector, and then use those values as our initial position. Add another set parameter module, and for this one, select the existing particle's position, then set it to an expression. We will spread the particles across the xy plane, so we can replace the first two terms of the declaration with the UVs, so our position ends up being the vector particles.uv.xy, 0. This kind of works, but remember that we are assigning a 0 to 1 value, so this square is only 1 unit wide. And we want the UVs to stay in that range, so let's scale the position with a new float user parameter. I call this one size, so we can reference it in the code using user.size. Now update this position code to be particles.uv.xy times user.size, 0. If we give this parameter a default value like 500, the particles should now be spread in a square of that size. Perfect. So when we're creating the particles, we're giving them a random UV value and use that to distribute them. But then we're going to move these particles, and once we do that, we don't want to use random UVs for our texture sample, but instead some coordinates based on the current particle position. To do this, we basically need to repeat one of the previous modules, but in reverse. Add another set parameter, but this one placed in the particle update stage. Then, add the existing UV parameter and again set it to be an expression. The vector in this case will be particles.position.xy, but we have to divide it by the user.size parameter to remap it to the 0 to 1 range that we need on the UVs. Great, we are now ready to add our sample texture module. After doing so, you can drag and drop the render target from the content browser to assign it, and set the UV position to be our particle's UV property. If we want to visualize the sample value, we can add a color module and set it an expression to be this float4 vector. Particles.sampletexture.samplecolor.xyz, 1. The reason why we are not using the full sample is because we didn't add an alpha field to the render target texture, so we are only taking the RGB components and setting the alpha to be 1. Okay, this is probably hard to see against the bright default environment map, but the particles now have the colors from the render target, so we know it's working. We can disable or remove the color module now and use the sample to move the particles instead. Add another set parameter with an expression, this one for the particle's velocity. We could set this one to the same value that we just tested as color, in our case particles.sampletexture.samplecolor.xyz, but for our velocity we only want the first two components, so let's use xy, 0. This would also allow us to use the blue or the alpha channels to store other properties to pass to the particles in the future. Finally, since we are using velocities, we have to add a solve forces and velocity module, otherwise the particles won't move. If we play the timeline, technically the particles are moving, but we have the same issue that we had with the size earlier. The velocities are in a tiny range, so the particles barely move each frame. Let's fix this the same way that we did before, by adding a user parameter to scale the velocity, multiplying it by the sample value in the expression. It doesn't have to be a huge number, something like 10 or so will be fast enough for this size. This will allow us to choose how slow or fast the particles converge on the lines, and easily change that parameter from the main scene viewport. Excellent, now we have our effect going. One thing to note, is that there are no interparticle collisions, so after a while, many particles merge into single points on the lines. There are experimental modules to solve this in Niagara, using neighbor grids, but it is still not a viable option for this large number of particles. There are a few ways to add noise to the particle motion, for example using a curl noise, or alternatively you could change the base Chladni material to blend a noise texture there, or even use the original scalar field to add randomness around the line centers. Another option would be to use the vector as force instead of velocity, as I'm showing off here, but if you let it run for long enough, some particles tend to leave the boundaries. You could then counter these with a point attraction force or other methods, but all of this is beyond the scope of this tutorial. I'm sure that if you made it this far, you can easily extend and improve on the basic idea of this effect. I prefer the original set velocity that I started with, so I will disable the linear force and go back to that setup before we move on to the last part of this video. We are going to change the renderer type from sprites to meshes, but the cube that I will use for demonstration purposes is too large, so I'm going to set the mesh scale in the initialize particle module before swapping the renderers. I'm using the editor cube, but you can easily create some low poly pebbles or stones with different materials if you want the effect to resemble some of the reference photos and video more closely. And we are almost there. The last thing that we will add is some rotation to the meshes. If you look closely, the particles are simply sliding towards the target, but we want them to roll like they do on the references. If we add an update mesh orientation module, Niagara has this useful method called rolling orientation, which rotates the particles an amount based on the distance moved and an axis based on the direction. This basically makes them roll like spheres, which is a good approximation for this particle size and looks great in motion. And with this, I think we're done with today's tutorial. Thank you for watching this video. I hope you had a good time and learned something that you can use in your projects. If you did, don't forget to do the like and subscribe thing and leave a comment below if you have questions or suggestions for future videos. See you next time!